Alright, we're going to have a bit of discussion on how to analyze multiple wavelengths in a laser beam. In other words, we have multiple wavelengths running collinear and simultaneously. We're going to start with the easiest example, but what we'll learn from this example we'll be able to carry over to the more complex analysis dealing with more wavelengths and outside particular spectral regions. We'll get to what we mean by all that in just a little bit. First, let's just start with two visible wavelengths. So we're going to start with a laser beam that has a 532 wavelength and a 650 wavelength, nanometer wavelength running simultaneously, collinearly, and they both have 10 milliwatts. So let's start by analyzing one at a time. And we'll go to nanometers, we'll do 532, come down here and we will put 10 milliwatts. Okay. Now we're going to use the ANSI default of a 1/4 of a second exposure. Right. And the 1/4 second exposure comes from our aversion response, which we're allowed up to 1 milliwatt. Now we're going to do this with a small beam with the observer set at observer distance set at 0. Okay, so we know that the percent transmission is 100% through the limiting aperture, and that's what we want. We'll notice that for our observer we need an OD of 1. Okay, what's really going on here is that this eyewear, if you bought exactly one, will leak 1 milliwatt. Remember, this is a class 2, we're allowed up to 1 milliwatt, and so the eyewear will leak 1 milliwatt, relying on your aversion response to work. Okay, so we've looked at the 532 wavelength and we see that we need an OD1 for that. Let's look at, well, before we move there, let's look at the MPE. Yep, 2.55 milliwatts per square centimeter. Okay, now we know that's going to be the same because in the visible from 400 to 700 the MPE is always the same. Okay, 2.55 milliwatts per square centimeter. And we'll notice then, because really it's the MPE that drives everything here, that nothing has changed. You need an OD1 at 650. Alright, but that's what we just did is an analysis for each wavelength. Okay, it doesn't tell us how they're acting in concert. So here's a couple of questions we ask ourselves. One, the first one, what is the absorber? Well, in both of these wavelengths, the absorber is the retina, so they will act in concert. They act together. All right. Next, what's the MPE? Well, the MPE is the same for both of them, so they behave in an identical manner when they're absorbed at the retina. Okay, as far as the MPE is concerned, our safe biological limit. So we should be able to just put these two wavelengths together into one wavelength and treat them as one. Same MPE, 10 milliwatts, so we'll stay with 650, it doesn't matter which visible wavelength we go with, and we will go to 20 milliwatts, e to the minus 3, and we'll notice that our OD went to 1.3. That is the OD required across the range of 532 to 650. Okay, why 1.3 instead of 1? Well, it's taking into account both wavelengths acting at the retina at the same time. Now there's another little way we can look at this, if you will, and that's say, well, okay, if each wavelength by itself needs an OD of 1, but each filter at an OD of 1 leaks 1 milliwatt, that means that out of both of these wavelengths, we're getting 2 milliwatts. Let's put 2 milliwatts in. Okay, and we're going to see that to cover 2 milliwatts we need an OD of 0.31. 1 milliwatt we don't need an OD, and I might tell you that the actual value for class 2 level 1 milliwatt is rounded. It's really let's see if I get this right, 0.98 e to the minus 3, and that pretty much takes us down to 0. We'd need to go just a little bit less to get the NOHD down, but that's really not a concern. You'll see that the OD at the observer range is 0, at the observer distance is 0. Okay, so at 1 milliwatt we really have no OD, but at 2 milliwatts, okay, we have a 0.3. So that tells us that we have the one OD for each wavelength, or per wavelength, 532 to cover the 532. Then we need an extra 0.3 to take care of that 1 milliwatt extra that's being leaked through the eyewear. So the total OD value across the range of 532 to 650 would be 1.31 OD. Okay. Now the thing we want to remember here is that the MPEs were the same. If we were going to make a power adjustment, which we're going to talk about how we adjust the power when the wavelengths don't have the same MPE, but we want to look at them as if it was a single wavelength, we're going to be using a ratio of the MPEs. So here the ratio is 1. So if we had 10 milliwatts in 650 and we were pushing it to the 532 wavelength, we'd say, well, the 532 has 10 milliwatts, the 650 has 10 milliwatts plus, okay, times the ratio of the MPEs, which is 1, so that's 10 times 1, so it's 20 milliwatts. So in that case, we'd go, okay, we're pushing it all to the 532, 20 milliwatts, and an OD across the range of 532 to 650 of 1.31. Okay? All right. This is part 1. Part 2 will be coming up a little later, so look for the posting.